6 million years ago, there were no humans anywhere on Earth. There were forests stretching across parts of Africa, broken by expanding grasslands that had not existed for very long. Small groups of apes moved through both worlds, unaware that the landscape around them was beginning to change. Some stayed where their ancestors had always lived. Others wandered into places they had never needed to survive before. That choice changed everything. Over the millions of years that followed, those early apes learned to walk upright across open ground. Their hands became free. Their brains grew larger. They learned to shape stone, master fire, cross oceans, paint cave walls, and eventually ask where they themselves had come from. But none of it was guaranteed. Our story is filled with branches that ended, entire human species that disappeared, populations reduced to the edge of extinction, and moments when a slightly different climate, a different migration, or a different decision could have left the world without us. Every person alive today still carries that journey. It is written into the shape of our feet, the curve of our spine, the way our hands move, and even the way our eyes meet another person's across a room. Today, we're following that journey from the first forest apes to the only human species left on Earth, tracing the discoveries, catastrophes, and unlikely turns that shaped every one of us. Now relax, and let's go back to Africa, where it all began. Africa had already begun rewriting its own landscape long before any creature could understand the meaning of those changes. Between roughly 7 million and 6 million years ago, during the late Miocene, climates across much of the continent shifted toward increasing dryness. Woodlands that had once stretched across broad regions gradually became interrupted by expanding grasslands and scattered savanna. Rivers changed course, lakes appeared and disappeared, and familiar habitats fractured into smaller pockets. Every alteration reshaped the opportunities available to the animals living there. Among those inhabitants was a population of apes whose descendants would eventually follow different paths. Evidence preserved in fossils, together with comparisons of deoxyribonucleic acid among living species, indicates that both modern chimpanzees and humans trace their ancestry to this shared population in Central and East Africa. The separation between those lineages is estimated to have occurred around 6 million to 7 million years ago through analyses of accumulated genetic changes across countless generations. From that point onward, each lineage adapted to different ecological pressures, gradually becoming something neither ancestor had ever been. The fossil record preserves only scattered fragments from those earliest chapters. Yet each discovery adds another piece to the larger picture. One of the oldest candidates is Sahelanthropus chadensis, uncovered in Chad and dated to between 6 million and 7 million years ago. Another, Ororuntuchinensis from Kenya, lived around 6 million years ago. Later came Ardipithecus ramidus from Ethiopia, dating to about 4,400,000 years ago. None looked fully human, nor entirely like modern apes. Their skeletons reveal an intriguing blend of traits carried from different ways of life. Those early members of the human lineage still climbed with confidence. Curved fingers and flexible shoulders remained well suited for moving among branches, while changes in the pelvis, legs, and feet hinted that time spent on the ground was steadily increasing. Evolution rarely abandons an old design all at once. It reshapes existing structures little by little, allowing familiar abilities to persist while new ones gradually emerge. These creatures occupied an intermediate world where forests and open country both played important roles in daily survival. Across eastern Africa, another force added further complexity. The Great Rift Valley formed an immense chain of valleys, lakes, volcanoes, and rising highlands that stretched across the landscape. Shifting waterways and changing terrain repeatedly divided populations into smaller groups, only for changing climates to reconnect them generations later. Periods of separation encouraged distinctive characteristics to develop, while later contact sometimes blended those differences together. Geography became an active participant in evolution, guiding populations along separate courses before allowing their paths to cross again. For that reason, the history of humanity resembles a branching shrub instead of a straight staircase. Numerous hominin species appeared, adapted to local conditions, and disappeared without leaving living descendants. Each branch represented a genuine experiment shaped by changing environments and inherited variation. The lineage leading to modern humans survived among many alternatives, carrying forward only one thread from a far richer tapestry whose missing branches still rest beneath African soil. Every lasting transformation begins with an ordinary movement repeated across countless generations. In the human lineage, that movement was a step taken on two legs. Around 4,400,000 years ago, the fossil remains of Ardipithecus ramidus reveal the earliest convincing evidence that upright walking had become a regular part of daily life. This was still an animal at ease among branches, yet its body had begun adapting to a new rhythm across the ground, balancing between two worlds without belonging entirely to either. One of the most remarkable records of that change survives far from any skeleton. In northern Tanzania, a layer of volcanic ash settled across the landscape around 3,600,000 years ago. Soon afterward, two individuals walked across its soft surface, leaving footprints that hardened as fresh layers covered them. Preserved within stone until their discovery millions of years later, those tracks reveal a familiar pattern. The heel touched first, weight rolled through the arch, and the toes pushed forward in sequence. The gait is strikingly similar to the one carried by every person today, connecting distant walkers through a single shared motion. Why this transformation unfolded remains one of the liveliest discussions in paleoanthropology. Several explanations may all contain part of the story. Standing upright freed the hands to carry food gathered across scattered landscapes, while parents could transport dependent young more efficiently during long journeys. A vertical posture also reduced the amount of the body exposed to the intense midday sun, while lifting the head higher above heated ground. Crossing open country demanded less energy on two legs than moving the same distance by knuckle walking, making travel between shrinking patches of woodland more economical. Taller posture also offered a broader view above tall grasses where potential predators or distant food sources could be detected earlier. Every advantage arrived with lasting compromises. The human spine gradually developed sweeping curves that helped balance the upper body, although those curves also placed greater mechanical stress upon the lower back. Knees shifted inward beneath the hips, supporting efficient walking while becoming more vulnerable to injury than those of four-legged mammals. The pelvis shortened and widened to stabilize each stride, creating the foundation for an entirely new style of movement that shaped every generation that followed. That same reshaped pelvis narrowed the birth canal, establishing an evolutionary tension that would persist for millions of years. As descendants eventually developed larger brains, childbirth became increasingly difficult because infant heads and maternal anatomy evolved under competing demands. The challenge never truly disappeared. It remains written into human biology, linking modern families with choices first made deep in prehistory. Standing upright also transformed the way the body managed heat. Raising the torso farther from the warm ground improved air circulation, while reducing direct sunlight striking much of the body during the hottest hours. More efficient sweating became an increasingly valuable cooling system, accompanied over time by the loss of much of the dense body hair common among earlier ancestors. The newly available hands did not immediately produce crafted stone tools. Nearly 2 million years would pass before such evidence appeared. Their freedom arrived first, waiting patiently for possibilities that evolution had not yet revealed. For nearly 2 million years, the story of the human lineage unfolded through an extraordinary collection of upright apes whose futures diverged in many directions. Between roughly 4 million and 2 million years ago, the Australopithecines became the dominant hominins across parts of Africa. They walked confidently on two legs, yet their minds remained only modestly larger than those of modern chimpanzees. Evolution was exploring many possibilities at once, producing populations that shared common ancestry while adapting to different landscapes and sources of food. Among these relatives, one individual has become especially familiar. In 1974, researchers working in Ethiopia uncovered the partial skeleton of a female later named Lucy, belonging to the species Australopithecus afarensis. Dated to approximately 3,200,000 years ago, her remains represented about 40% of a complete skeleton, making her the most complete early hominin known at that time. Although countless discoveries have followed, Lucy continues to provide one of the clearest windows into this long chapter of human evolution. She stood around 1.1 meters tall, which is about 3.6 feet, and weighed close to 29 kilograms. Her proportions revealed a body balancing two different lifestyles. The hips, knees, and feet supported regular upright walking across the ground, while long arms, curved finger bones, and mobile shoulders remained well suited for climbing. Trees still offered food, shelter, and protection, even as increasing time was spent moving between them across open terrain. The body carried no sense of contradiction. Each feature reflected practical solutions to the varied demands of everyday survival. Inside the skull, however, change was unfolding at a far slower pace. Australopithecus afarensis possessed a brain measuring roughly 380 to 430 cubic centimeters, far smaller than the modern human average of approximately 1,350 cubic centimeters. Intelligence should not be measured by size alone, yet the comparison illustrates how much of the familiar human mind still lay far in the future. These early walkers had mastered one major transformation, while many others remained unwritten. Lucy was only one member of a much larger family. Australopithecus africanus occupied southern Africa, while Australopithecus sediba appeared much later, with a distinctive blend of primitive and more human-like characteristics. Alongside them lived the robust forms now placed within the genus Paranthropus, including Paranthropus robustus and Paranthropus boisei. Their enormous chewing muscles and broad grinding teeth allowed them to process hard seeds, fibrous plants, and other difficult foods that challenged many neighboring species. This specialization supported their survival for more than 1 million years before the entire branch eventually disappeared. Viewed together, these species reveal evolution working through parallel experiments instead of following a predetermined destination. Different body shapes, diets, and ecological strategies coexisted across the continent, each responding to local conditions through countless generations. The lineage leading toward modern humans occupied only one branch among many, carrying no obvious sign that it would outlast the others. Around 2,800,000 years ago, a jaw fragment discovered in Ethiopia hinted at the earliest members of the genus Homo, although researchers continue to debate exactly where the boundary between late Australopithecines and those first humans should be drawn. A sharp edge can alter the course of evolution as profoundly as any change in climate or anatomy. At some point, an early hominin lifted one stone, struck it against another, and discovered that fractured rock could become something entirely new. That simple act marked the beginning of a technological tradition that would continue without interruption into the present day, each generation inheriting ideas that could outlast the individuals who first imagined them. In 2015, researchers announced a remarkable discovery from the Lomakwi 3 site in Kenya. The stone artifacts recovered there were dated to approximately 3,300,000 years ago, extending the known history of toolmaking by roughly 700,000 years beyond previous estimates. Their age places them within the era of the Australopithecines, suggesting that deliberate tool production began long before the appearance of the earliest members of the genus Homo. The stones themselves are large and rough in appearance, lacking the refinement seen in later technologies, yet they bear unmistakable signs of purposeful shaping. These earliest implements were created by striking one rock against another until flakes broke away, leaving cutting edges capable of slicing plant material or animal tissue. Their makers were not producing elegant forms. They were discovering that fractured stone possessed useful properties unavailable in untouched rock. Even without symmetry or careful finishing, those edges represented a practical extension of the hand, expanding what muscles and fingernails alone could accomplish. Around 2,600,000 years ago, another tradition emerged that displayed greater consistency and planning. Known as the Oldowan industry, after Olduvai Gorge in Tanzania, where Dr. Louis Leakey and Dr. Mary Leakey conducted pioneering studies during the 1930s, these tools reveal minds working several steps ahead. Toolmakers selected suitable raw materials such as flint, obsidian, and quartzite instead of gathering stones at random. Some rocks were even carried from their original locations before being shaped, showing that useful resources could be recognized, remembered, and transported for future tasks. Producing an Oldowan tool demanded more than physical strength. The maker needed to picture the desired flake before the first strike landed, judge the angle of impact, and adjust each blow according to the changing shape of the stone. Such work relied upon planning, spatial awareness, and working memory. Every successful tool embodied a sequence of decisions preserved within its fractured surfaces, offering one of the earliest archaeological records of increasingly sophisticated thought. The stones alone tell only part of the story. At many excavation sites, archaeologists have also uncovered animal bones bearing narrow cut marks that differ clearly from the tooth marks left by carnivores. These traces indicate that early hominins used stone flakes to remove meat from carcasses, including those of enormous animals such as hippopotamuses and elephants. Whether these creatures were hunted or found after predators had finished feeding remains actively debated. Current evidence favors scavenging, with hominins arriving later to harvest nutritious flesh and, most importantly, the rich marrow sealed inside heavy bones. That new source of concentrated calories carried consequences reaching far beyond a single meal. Bone marrow and meat supplied far more energy than many plant foods, helping support organs with especially demanding nutritional needs. As brains gradually became larger across later generations, dependable access to high-energy foods may have reinforced further cognitive expansion. Stone tools and growing intelligence began shaping one another, forming a partnership that would accompany the human lineage for millions of years. No fossil reveals a thought, a memory, or an idea. Bones preserve shape, while the experiences that once filled a living mind disappear with the passing of time. Even so, The expanding chambers inside ancient skulls tell a remarkable story. Between roughly 2 million years ago and 200,000 years ago, the hominin brain underwent one of the fastest increases in size ever recorded among vertebrate animals. Early members of the genus Homo possessed brains measuring around 450 cubic centimeters. By the time of late Homo heidelbergensis, average brain volume had reached nearly 1,500 cubic centimeters. This transformation did not unfold as a smooth upward climb. Fossil evidence suggests that brain growth accelerated during particular intervals, separated by long periods of relative stability. Many of those bursts coincide with episodes of climatic instability when changing rainfall, shifting vegetation, and unpredictable food supplies repeatedly altered the challenges facing hominin populations. Adaptability became increasingly valuable. Individuals capable of solving unfamiliar problems or adjusting behavior to changing conditions often gained advantages that accumulated across many generations. Such expansion carried an extraordinary biological cost. The brain demands more energy than any other organ in the human body. In modern humans, although it accounts for only about 2% of total body mass, it consumes roughly 20% of the calories used each day. Every increase in brain size therefore required dependable access to richer sources of nutrition. The gradual incorporation of meat, marrow, and eventually more efficient food processing helped provide the steady flow of energy needed to support this demanding tissue. Growth also changed the internal organization of the brain. The neocortex, the outer layer responsible for language, planning, abstract reasoning, and social understanding, expanded more rapidly than many deeper structures. The significance lay not only in having a larger brain, but in reshaping how different regions communicated with one another. Additional surface area created opportunities for more intricate networks of connections, allowing information from memory, perception, and decision making to interact in increasingly flexible ways. The skull itself adapted to these internal changes. Faces gradually became flatter. Heavy brow ridges became less pronounced in many later hominins, and the cranium expanded upward and backward to accommodate growing brain tissue. These visible changes reflected an ongoing negotiation between existing anatomy and new developmental demands. Evolution rarely discards old structures entirely. Instead, it remodels them generation after generation until familiar forms acquire unfamiliar functions. Some researchers propose that survival in changing environments explains much of this remarkable expansion. Others place greater emphasis upon life within increasingly complex social groups. This idea, known as the social brain hypothesis, suggests that remembering relationships, recognizing individuals, understanding intentions, resolving conflicts, and maintaining cooperation required immense cognitive capacity. Every companion represented a constantly changing source of information, making social life one of the most demanding environments an intelligent animal could inhabit. Comparisons among living primates lend support to that perspective. Species living in larger social groups generally possess proportionally larger neocortices than closely related species with simpler social structures. The pattern appears more closely linked to group size than to environmental complexity alone. As hominin communities became richer in cooperation, competition, learning, and shared experience, natural selection may have increasingly favored brains capable of navigating those intricate relationships. Within expanding networks of minds, intelligence itself became part of the environment, shaping the evolution of every generation that followed. A newborn human enters the world carrying remarkable potential, yet possessing very little independence. Compared with every other living primate, the human infant is the most neurologically immature at birth. A baby's brain measures only about 1/4 of its eventual adult size, while a newborn chimpanzee begins life with nearly 45% of its adult brain volume already developed. Much of what becomes the human mind is constructed after birth, during years spent surrounded by other people. This unusual beginning emerged from a compromise written into the body long before the first human child was born. As upright walking reshaped the pelvis over millions of years, the birth canal became narrower. At the same time, expanding brains produced increasingly larger infant heads. Those two trends could not continue without limitation. Birth therefore shifted earlier in development, allowing babies to pass safely through the pelvis before their brains reached full size. The remaining growth unfolded outside the womb, protected within families and communities instead of within the mother's body. Such an arrangement transformed childhood into the longest developmental period found among primates. Human offspring require approximately 12 to 15 years of sustained care before reaching reproductive maturity. During those years, they must be fed, protected, guided, and taught. No single adult could reliably meet every one of those demands under the conditions faced by prehistoric hunter gatherers. Raising children gradually became a shared responsibility extending beyond parents alone. Anthropologists describe this pattern as cooperative breeding. Grandparents, older brothers and sisters, aunts, uncles, and unrelated members of the community all contributed food, protection, supervision, and knowledge to children who were not necessarily their own direct descendants. Human survival became woven into relationships that stretched across generations. An infant growing within such a network received far more than nourishment. Each interaction offered opportunities to observe faces, voices, gestures, and social expectations that shaped the developing brain itself. One influential explanation for this pattern is known as the grandmother hypothesis, proposed by researcher Kristen Hawkes. Unlike most other primates, human females commonly survive for many years after their reproductive lives have ended. According to this hypothesis, grandmothers increase the survival of grandchildren by gathering food, sharing experience, and supporting their daughters during the demanding years of child rearing. Families benefiting from such assistance could successfully raise more surviving offspring, gradually favoring longer human lifespans through natural selection. Living within cooperative groups also introduced demanding cognitive challenges. Individuals needed to remember who had shared food, who had cared for children, who could be trusted, and who repeatedly accepted help without returning it. Reciprocity became an important part of everyday survival. Social relationships required careful attention, encouraging increasingly sophisticated communication, emotional understanding, and memory. Language itself may have flourished within these growing networks, allowing experience and practical knowledge to pass efficiently between generations. The human child, therefore, develops through an unusual partnership between biology and culture. The brain arrives prepared to learn, while family and community provide the knowledge that fills it. Speech, customs, practical skills, beliefs, and accumulated experience become part of development during childhood instead of being inherited directly through genes. Every generation begins life dependent upon those who came before, carrying forward an expanding inheritance that exists within minds as much as within the body itself. Among all the discoveries made by the human lineage, few transformed daily life as completely as learning to keep a flame alive. Fire had always existed in nature. Lightning ignited forests. Volcanic eruptions scattered burning material across the landscape, and dry grasslands occasionally erupted into walls of flame. For countless generations, hominins could only observe these events from a distance. Eventually, one population crossed a remarkable threshold by preserving, tending, and controlling a force that no other animal had mastered. The earliest widely accepted evidence of controlled fire comes from Wonderwork Cave in South Africa, where burned fragments of bone and plant ash have been dated to approximately 1 million years ago. These remains were discovered deep inside the cave, well beyond the reach of naturally spreading wildfires. Their location strongly suggests that hominins deliberately carried burning material into the shelter and maintained it there. Earlier hints of fire use exist, including burned bones from sites in Kenya dating to around 1,500,000 years ago. Yet, those discoveries remain open to debate because natural fires cannot be ruled out with complete confidence. Control of fire altered food in ways that transformed biology itself. Primatologist Richard Wrangham proposed the cooking hypothesis, arguing that cooking became one of the driving forces behind later human evolution. Heat softens plant fibers, breaks down connective tissues in meat, destroys many harmful microorganisms, and allows the digestive system to extract more energy from every meal. Food that once demanded prolonged chewing and digestion became easier to process, leaving more calories available for the growing body, and, especially, the increasingly expensive brain. Changes preserved in the fossil record support this possibility. Homo erectus, appearing around 1,900,000 years ago, possessed noticeably smaller teeth than many earlier hominins, along with a reduced digestive tract relative to body size. These anatomical changes fit well, with a diet relying more heavily upon cooked foods that required less grinding inside both the mouth and the intestines. The body itself gradually reflected the changing relationship between nutrition and technology. As daylight faded each evening, another transformation unfolded around glowing embers. Fire extended activity beyond sunset, creating opportunities for families and companions to remain together after darkness settled across the landscape. The circle surrounding a hearth became a place where experience could be shared through spoken language, practical skills demonstrated, and memories carried from one generation into the next. Knowledge no longer depended entirely upon observation during daylight hours. It could also be preserved through conversation after the day's work had ended. Fire also expanded the boundaries of where hominins could survive. Regions that once became dangerously cold after sunset now offered shelter through controlled warmth. Seasonal movements into cooler environments became increasingly practical because people could reshape local conditions instead of adapting only through changes within their own bodies. Fire represented the first technology capable of modifying the surrounding environment in a sustained and predictable way. Even patterns of sleep may have shifted. Resting beside a protected fire reduced the danger posed by many nocturnal predators and offered greater comfort on the ground than earlier sleeping places among branches. Some researchers suggest that this security encouraged deeper stages of sleep rich in rapid eye movement, supporting memory, creativity, and learning. Although many details remain under investigation, the partnership between humans and fire became one of the defining relationships in the entire history of our species, changing bodies, societies, and minds through the steady light of a carefully tended flame. A different kind of traveler entered the story around 1 million 900,000 years ago. Earlier hominins still carried many reminders of a life divided between branches and open ground. Homo erectus displayed a body that belonged almost entirely to the landscape below the trees. Long legs lengthened each stride. The chest became broader and barrel shaped, and the proportions of the body shifted toward a form that would appear strikingly familiar today. Inside the skull, the brain averaged around 900 cubic centimeters, noticeably larger than that of earlier members of the human lineage. One remarkable discovery brought this transformation into unusually clear focus. In northern Kenya, researchers uncovered the skeleton known as Turkana boy during the 1980s. Dated to approximately 1,500,000 years ago, he died at about 8 years of age, yet already stood around 160 centimeters tall, which is about 5 feet 3 inches. Had he reached adulthood, researchers estimate he might have grown to about 185 centimeters, which is about 6 feet 1 inch. His bones reveal a body designed for covering long distances with an efficient, upright stride that demanded far less energy than shorter limbed ancestors. This new anatomy made movement across continents increasingly possible. Fossils show that Homo erectus became the first hominin to leave Africa in sustained migrations. Individuals reached the region now called Georgia by approximately 1,800,000 years ago, settled on the island of Java by roughly 1,600,000 years ago, and eventually occupied northern China, where fossils from Zhoukoudian cave date to around 780,000 years ago. Their expansion demonstrates an adaptability that earlier hominins had never achieved, carrying the human story across forests, grasslands, mountains, and changing climates. The discoveries at Dmanisi in Georgia introduced another important lesson. Between the 1990s and the early years of the 21st century, researchers uncovered 5 skulls that differed markedly from one another in size, facial structure, and cranial shape. At first glance, they might have appeared to represent several distinct species. Because they were found together within the same population, many researchers concluded that early members of the genus Homo may have displayed a much broader range of natural variation than previously recognized. Some fossils, once assigned to separate species, could instead represent ordinary diversity within a single evolving lineage. The body of Homo erectus also tells the story of endurance. Sweating efficiently across nearly hairless skin allowed excess heat to escape during prolonged activity beneath the tropical sun. Long legs and resilient tendons supported steady travel across great distances without exhausting valuable energy reserves. These characteristics gave rise to the idea of persistence hunting, in which hunters followed an animal for many hours until overheating gradually weakened its ability to escape. Success depended less upon bursts of speed than upon patience, coordination, and physical resilience. Perhaps the most extraordinary measure of Homo erectus lies in its longevity. This species endured for well over 1,500,000 years, surviving far longer than Homo sapiens has existed so far. Across that immense span of time, countless generations adapted to shifting climates and unfamiliar landscapes while maintaining a body plan that proved remarkably successful. Their footsteps stretched across continents, leaving behind a durable foundation upon which every later chapter of human evolution would continue to unfold. Around 1,760,000 years ago, stone tools began to display a striking new level of refinement. Earlier cutting flakes had served many purposes, yet this new creation reflected something beyond immediate necessity. Craftsmen shaped stone into a balanced, teardrop form with edges running along both sides. Producing such an object required removing dozens of flakes in a carefully planned sequence. Each strike changed the shape of the stone, and every following strike depended upon those that had come before. The finished hand axe carried evidence of foresight long before the final edge appeared. Despite its familiar name, the Acheulean hand axe was not limited to a single task. It functioned as a versatile companion for everyday survival across the changing landscapes of the Pleistocene. Its sharpened edges sliced meat from animal carcasses, scraped hides for clothing or shelter, chopped branches, uncovered nutritious tubers, and cracked bones to reach the rich marrow inside. A single well-crafted tool could remain useful through many different activities, reducing the need to produce separate implements for each challenge encountered during daily life. The craftsmanship behind these tools reveals something equally important about the minds that created them. Before striking the first blow, the maker needed to imagine the finished object as a complete three-dimensional form. Suitable stone had to be selected for its strength and predictable fracture pattern. Every removal altered the remaining surface, demanding constant adjustment and careful judgment. Mistakes could not always be repaired, making each decision increasingly important as the work progressed. These abilities reflect forms of planning, spatial reasoning, and flexible problem solving that are closely associated with the expanding frontal regions of the human brain. Remarkably, this technological tradition endured for approximately 1,500,000 years, with only gradual changes. Few inventions in human history have remained useful for such an immense span of time. The consistency suggests that knowledge passed from one generation to another through observation, imitation, and teaching. Young individuals almost certainly watched experienced toolmakers, learning where to strike, how to judge stone quality, and how to recognize a successful shape before attempting the process themselves. The hand axe became more than an object, it became a shared tradition carried across countless lifetimes. Its distribution also tells an intriguing story. Acheulean tools appear across much of Africa, Europe, and Western Asia, yet they are largely absent from Eastern Asia, where populations often continued using simpler flake tools. Researchers continue exploring several possible explanations. Suitable raw materials may have differed from one region to another. Cultural traditions may have followed separate paths, despite belonging to related populations. Geographic barriers may also have limited the spread of particular manufacturing techniques. Each possibility reminds us that technological history does not always advance along a single, universal route. Around 300,000 years ago, the Acheulean tradition gradually gave way to the more varied toolkits of the Middle Stone Age. Stone implements became smaller, more specialized, and increasingly adapted to particular tasks. This transition unfolded alongside the emergence of anatomically modern humans, linking changes in technology with changes in biology. New minds were shaping new tools, while inherited knowledge continued flowing across generations. The familiar hand axe, after serving humanity for more than 1,000,000 years, yielded its place with lasting influence, still embedded in every carefully planned invention that followed. Earth did not settle into a single frozen chapter during the Pleistocene. From about 2,600,000 years ago until roughly 11,700 years ago, the planet shifted through repeating cycles of advancing ice and returning warmth. These glacial and interglacial periods followed a rhythm of approximately 100,000 years, shaped by subtle variations in Earth's orbit around the sunday. Each cycle altered landscapes, coastlines, rainfall, and vegetation, ensuring that no generation could assume the world would remain as it had always known it. During the coldest intervals, immense ice sheets spread across much of North America and northern Europe. So much water became locked within glaciers that global sea levels fell by as much as 120 meters, which is about 394 feet. Land bridges emerged where oceans had once separated continents, opening pathways for animals and human relatives to move into unfamiliar territory. Elsewhere, familiar habitats contracted. African grasslands repeatedly expanded and retreated, dividing populations before later reconnecting them as climates shifted once again. Every change rearranged the map of opportunity. Some researchers suggest that this constant uncertainty became one of evolution's greatest teachers. Paleoanthropologist Richard Potts proposed the variability selection hypothesis, arguing that no single climate produced the qualities that define humanity. Instead, repeated environmental instability favored individuals capable of adapting to changing conditions. Those able to alter their behavior, broaden their diets, explore unfamiliar environments, or develop new solutions gained an advantage whenever familiar resources disappeared. Flexibility itself became an increasingly valuable inheritance, preserved across countless generations, facing landscapes that rarely remained predictable for long. Isolation played its own part in this long process. During difficult climatic periods, groups often survived within scattered refuges where water, food, and shelter remained available. These separated populations gradually accumulated their own genetic differences and cultural traditions. When warming climates reopened migration routes, distant relatives encountered one another once again. They exchanged genes, tools, and learned behaviors, blending innovations that had developed independently. Human evolution therefore unfolded through repeated cycles of separation and reunion, each leaving subtle traces within the growing diversity of our lineage. The Sahara offers one of the clearest examples of this changing world. Today it forms one of the largest deserts on Earth, creating a formidable barrier between regions of Africa. Across the Pleistocene, however, increased rainfall transformed it several times into broad grasslands crossed by rivers and dotted with freshwater lakes. During these green Sahara intervals, animals and hominin populations traveled across landscapes that would later become arid sand. As rainfall declined, those pathways disappeared once more, closing routes that had briefly connected sub-Saharan Africa with northern Africa and the Middle East. Food sources shifted alongside these climatic rhythms. Expansive, cold grasslands supported enormous grazing mammals, including mammoths, woolly rhinoceros, and giant deer. These animals became valuable resources for Homo populations living across Europe and Asia. Securing such prey encouraged increasingly coordinated hunting, careful planning, and the development of weapons capable of striking from greater distances. Every successful hunt depended upon cooperation among many individuals, strengthening social bonds while rewarding communication and shared experience. Across these recurring pulses of cold and warmth, evolution did not follow a straight path. It advanced through continual adjustment, shaped by a world whose greatest constant was change itself. Evolution rarely follows a single road. More often, it resembles the growth of a great tree, where one sturdy trunk gives rise to several living branches, each reaching toward different horizons. Around 700,000 years ago, one such branching point appeared with the emergence of Homo heidelbergensis, a strongly built hominin whose place in human history occupies a remarkable position. This species stands near the last shared ancestor from which both modern humans and Neanderthals ultimately descended, while another closely related lineage would give rise to the Denisovans. The species takes its name from a fossil jaw uncovered near Heidelberg, Germany, during the early 20th century. Although that single discovery first drew attention, later finds across Africa and Europe revealed a far richer picture. Homo heidelbergensis possessed an average brain volume of around 1,200 cubic centimeters, approaching the lower range of many living humans. Broad shoulders, powerful limbs, and heavy muscle attachments suggest a body capable of enduring demanding landscapes where survival depended upon strength as much as endurance. Their appearance carried familiar human proportions while retaining several robust features inherited from earlier ancestors. As populations expanded across Africa, Europe, and parts of Asia, changing climates gradually separated groups from one another. Advancing ice sheets transformed travel routes and divided habitats for thousands of generations. Once isolated, each population continued evolving under different environmental pressures. African descendants eventually gave rise to Homo sapiens. European populations followed another path that produced the Neanderthals. Farther east, another branch became the Denisovans, known today mostly through fragments of bone and remarkable genetic discoveries preserved within living people across parts of Asia and Oceania. One ancestral population, therefore, became the source of several distinctly human stories unfolding at the same time. Evidence from the site of Schöningen in Germany offers a glimpse into the abilities these people possessed around 300,000 years ago. Archaeologists uncovered 8 carefully crafted wooden throwing spears, preserved within waterlogged sediments. Some measured as much as 2.5 meters, which is about 8.2 feet, and balanced in ways remarkably similar to modern athletic javelins. Producing such weapons demanded careful selection of timber, deliberate shaping, and an understanding of balance that could only emerge through experience and shared knowledge. Successful use also depended upon coordinated hunting, with individuals working together instead of acting alone. Another discovery deepens the picture still further. At Atapuerca in Spain, researchers uncovered a chamber containing the remains of at least 28 Homo heidelbergensis individuals dating to approximately 430,000 years ago. Many scientists interpret this remarkable accumulation as the earliest known example of deliberate disposal of the dead. Absolute certainty remains elusive, yet the evidence suggests that bodies were intentionally placed together rather than left where death occurred. Such behavior hints at a developing awareness that death carried meaning, extending beyond the immediate moment. Brain size alone never guarantees imagination, planning, or culture, yet Homo heidelbergensis demonstrates how closely biological potential and behavior had begun to converge. Some individuals possessed cranial volumes exceeding the average found among people today. Within those expanding brains, capacities for cooperation, craftsmanship, memory, and communication continued growing across countless generations. Before the familiar human world emerged, its essential foundations had already taken shape within this shared ancestor, whose descendants would eventually travel separate paths while carrying echoes of the same remarkable beginning. Across hundreds of thousands of years, another kind of human flourished beyond Africa, shaped by landscapes of snow, forests, mountains, and open grasslands. The Neanderthals emerged in Europe and Western Asia around 400,000 years ago and endured until roughly 40,000 years ago. Their stories stretched across a span nearly 3 times longer than Homo sapiens has existed. For much of that immense interval, they stood as one of the most successful human forms the world had ever known, adapting to climates that shifted again and again beneath the pulse of advancing and retreating ice. For generations, they were imagined as clumsy figures, burdened by limited intelligence, yet the fossil record has steadily erased that picture. Neanderthal brains averaged around 1,410 cubic centimeters, slightly larger than the average volume found in living humans, although the shape differed. Their skulls were longer from front to back, with prominent brow ridges and a lower, elongated cranium. Brain organization appears to have differed as well, suggesting that evolution can produce distinct forms of intelligence without following a single anatomical pattern. Size alone never determined thought, memory, or imagination. Compassion also leaves traces within stone and bone. One of the most remarkable examples comes from Shanidar Cave in present-day Iraq, where the skeleton known as Shanidar I belonged to an older man who lived despite extraordinary injuries. One arm had become severely withered, a leg fracture had healed, and evidence suggests he had lost vision in one eye. Survival under such conditions would have been nearly impossible without sustained assistance from others. Food, protection, and companionship must have been shared across many seasons, revealing social bonds capable of supporting individuals whose strength alone could no longer sustain them. Their relationship with death appears equally thoughtful, although the details continue to be examined carefully. At several sites across Europe and the Middle East, archaeologists have uncovered bodies placed in deliberate positions within prepared ground. Some graves contain objects that may have accompanied the deceased, though interpretations remain debated. Whether these practices reflected ritual, remembrance, or another tradition that has vanished with time cannot yet be determined with certainty. Even so, intentional burial suggests that death carried significance extending beyond the practical removal of a body from daily life. Other discoveries reveal minds capable of symbolic expression. Pieces of red ochre, an iron oxide pigment, have been recovered from Neanderthal sites older than the arrival of modern humans in Europe. Cave paintings at 3 locations in Spain have also been dated to periods preceding Homo sapiens on the continent, raising the possibility that Neanderthals themselves created some of these markings. If so, the impulse to leave symbols upon stone belonged to more than one branch of humanity, emerging through different populations connected by a shared evolutionary heritage. Their bodies reflected the demands of Ice Age environments. Compact limbs reduced heat loss, broad chests housed powerful lungs, and large noses helped warm freezing air before it reached the lungs. Strong muscle attachments reveal lives shaped by physical effort across demanding terrain. Although the Neanderthals eventually disappeared, they did not vanish entirely. When modern humans entered Europe and the Middle East between roughly 60,000 and 50,000 years ago, the two populations met and interbred. Today, people whose ancestry lies outside Africa still carry between 1 and 4% Neanderthal deoxyribonucleic acid, preserving within living cells a lasting connection to the humans we almost became. Sometimes an entire branch of humanity emerges from almost nothing at all. In the year 2010, a tiny fragment of finger bone recovered from Denisova Cave in southern Siberia revealed a discovery unlike any before it. The bone preserved deoxyribonucleic acid with extraordinary clarity, allowing researchers to reconstruct a complete genetic blueprint. That sequence belonged neither to modern humans nor to Neanderthals. It represented a human lineage that had remained entirely unknown despite countless years of exploration, a people whose existence had survived inside a single fingertip. The physical evidence for the Denisovans remains astonishingly sparse. Beyond that finger bone, only 3 teeth and part of a jaw discovered on the Tibetan plateau have been confidently identified. Such a collection could fit inside a small display case, yet it carries the weight of an entire species. In a remarkable reversal of traditional paleontology, scientists know far more about the Denisovan genome than about the shape of the bodies that carried it. Their faces, height, voices, and daily appearance remain only partially understood, while their genetic history has become one of the clearest among extinct humans. Those genetic records reveal that the Denisovan lineage separated from the ancestors of the Neanderthals around 400,000 years ago. From that point onward, their descendants spread across an immense region, extending from Siberia through eastern Asia and into parts of southeastern Asia. Such a distribution suggests remarkable adaptability across forests, mountains, grasslands, and changing climates. Their presence stretched across distances that would have connected many different environments, even though the fossil record has preserved only scattered traces of their passage. When modern humans expanded beyond Africa, these distant relatives were already established across much of that landscape. Encounters occurred often enough to leave an enduring mark within living populations. People from New Guinea and Aboriginal Australians carry approximately 4 to 6% Denisovan deoxyribonucleic acid, a proportion exceeding the Neanderthal contribution found in any present day population. These inherited sequences record encounters that took place tens of thousands of years ago, preserving biological memories that survived long after the Denisovans themselves disappeared from the fossil record. One inherited gift became especially important upon the high Tibetan plateau. Many people living above 4,000 meters, which is about 13,123 feet, possess a version of a gene known as endothelial pars domain protein 1. This inherited variation helps regulate hemoglobin production, allowing the body to use limited oxygen more efficiently at extreme elevation. Genetic studies show that this adaptation did not evolve independently within modern humans. It entered the human lineage through interbreeding with Denisovans, then spread because it offered a powerful advantage in mountain environments where thin air challenged every breath. Much about the Denisovans still escapes direct observation. Their settlements remain uncertain. The full span of their existence is still unfolding through new discoveries, and many fossils waiting beneath stone or soil may yet reshape their story. Their legacy demonstrates that an entire human species can remain nearly invisible until deoxyribonucleic acid reveals the hidden connections carried within living people. In that sense, the Denisovans endure less through bones than through inheritance, woven into the biology of millions whose bodies continue carrying fragments of an almost forgotten human journey. The shape of the modern human body appeared long before the full character of the modern human mind became visible in the archaeological record. Around 300,000 years ago, people whose skeletons would look strikingly familiar today lived in what is now Morocco. Fossils from Jebel Irhoud showed that anatomically modern Homo sapiens existed far earlier than once believed, extending the origin of our species by about 100,000 years beyond previous estimates. Their faces, limbs, and rounded skulls already resembled our own, although the material traces they left behind remained comparatively modest. For roughly the next 200,000 years, evidence of richly symbolic behavior appeared only in scattered glimpses. Stone tools continued to improve, families adapted to changing environments, and knowledge passed from one generation to the next. Even so, unmistakable signs of artistic expression, elaborate ornamentation, and complex cultural traditions remained uncommon. Then, Between approximately 100,000 and 40,000 years ago, the archaeological record changed with increasing speed. Decorative objects, carefully assembled weapons, pigments, engraved surfaces, and evidence of exchange across distant regions became more widespread, revealing minds that increasingly shaped the world through ideas as well as survival. One of the discoveries that transformed this understanding came from Layang Tidonge Cave on the island of Sulawesi in present-day Indonesia. There, a painting of a warty pig has been dated to at least 45,500 years ago. It currently stands as the oldest known figurative artwork discovered anywhere in the world. Its location proved just as significant as its age. Earlier assumptions placed the birth of figurative art in Europe, yet this remarkable image demonstrated that creative expression flourished far beyond that continent, suggesting that artistic thought emerged across different human populations rather than from a single cultural center. Even older indications of symbolic behavior come from Blombo's cave in South Africa. Archaeologists uncovered pieces of ochre engraved with deliberate geometric designs dating to about 75,000 years ago. Shell beads, fashioned as personal ornaments, extend from roughly 75,000 to 100,000 years ago, while a collection of ochre, bone, and shell containers formed a paint-making toolkit dating to approximately 100,000 years ago. These discoveries suggest that symbolic traditions accumulated gradually, each generation preserving ideas while adding new layers of meaning for those who followed. Exactly what sparked this remarkable flowering of behavior remains one of the enduring questions in human evolution. Some researchers propose that subtle genetic changes strengthened language or abstract reasoning. Others suggest that growing populations reached a point where knowledge could accumulate instead of repeatedly disappearing. Another possibility points toward recovery after a severe population decline, where surviving communities exchanged ideas more efficiently and preserved innovations with greater consistency. None of these explanations fully resolves the question, and each continues to inspire careful investigation. Whatever combination of forces shaped this transformation, its legacy reached beyond paintings, ornaments, or tools alone. Humans increasingly stored knowledge outside the mind through objects carrying shared meaning. Art preserved memory, ornaments expressed identity, and symbols connected individuals across generations. Culture itself became an inheritance, growing alongside biology until every new child entered not only a family, but also a world already filled with stories, traditions, and imagination waiting to be learned. Far to the northwest of the island now called Sumatra, the land once released a force that exceeded anything witnessed during recorded human history. Around 74,000 years ago, the Toba supervolcano erupted with extraordinary violence, sending an estimated 2,800 cubic kilometers, which is about 672 cubic miles, of ash, rock, and volcanic material into the atmosphere. For comparison, the eruption of Mount Tambora in the year 1815 expelled about 160 cubic kilometers, which is about 38 cubic miles. Toba released more than 17 times that amount, leaving a mark across much of southern Asia that can still be traced in layers of ash preserved beneath the ground. The eruption transformed far more than the landscape surrounding the volcano. Sulfur dioxide rose into the stratosphere, where it formed reflective particles that reduced the sunlight reaching Earth's surface. Climate models suggest that average global temperatures may have fallen by around 3 degrees Celsius, or 37 degrees Fahrenheit, to 5 degrees Celsius, or 41 degrees Fahrenheit, for several years. Some regions may have experienced cooling approaching 15 degrees Celsius or 59 degrees Fahrenheit. Forests, grasslands, and freshwater systems likely responded in different ways across the continents, changing the availability of plants and animals that human communities depended upon. Whether these environmental changes pushed humanity to the edge of extinction remains one of the most enduring debates in paleoanthropology. Modern humans possess remarkably little genetic diversity compared with other great apes. One explanation proposes that our ancestors passed through a severe population bottleneck, leaving only a relatively small number of breeding individuals. Genetic studies have suggested a surviving population somewhere between 10,000 and 30,000 breeding people. Every generation that followed would have descended from that limited ancestral pool, carrying only a fraction of the diversity that had once existed. The timing of this proposed bottleneck overlaps strikingly with the eruption of Toba. That coincidence inspired the idea that volcanic winter dramatically reduced human numbers across Africa and Asia. Under this interpretation, scattered groups survived in favorable regions, while many others disappeared, leaving only a handful of connected populations to rebuild the species. The genetic signatures preserved within living people may still carry the imprint of that distant reduction, although they cannot identify its exact cause on their own. Other discoveries encourage greater caution. Archaeological sites in the Indian subcontinent contain stone tools both below and above the volcanic ash deposited by the eruption. The continuity of these occupations suggests that at least some communities endured the environmental disruption without vanishing. Their survival indicates that the effects of Toba were probably uneven, with some landscapes suffering severe ecological stress, while others continued to support human life. This evidence reminds researchers that ancient disasters rarely produced identical outcomes across an entire continent. Whatever the precise sequence of events, the broader story remains remarkable. If humanity truly passed through a narrow demographic passage during this period, recovery unfolded with extraordinary speed. Within roughly 4,000 years, populations expanded once more, spreading across changing environments with renewed resilience. Every family alive today traces its history through that distant chapter, whether the bottleneck arose from volcanic catastrophe, another environmental challenge, or several pressures unfolding together. The debate continues, yet the survival of our species stands as the lasting consequence of that uncertain age. A path that began within one continent gradually reached nearly every shore on Earth. Around 70,000 to 60,000 years ago, a relatively small population of anatomically modern Homo sapiens left Africa in what genetic evidence identifies as the founding migration of all living people outside the continent. Estimates suggest that this traveling population may have included as few as 1,000 to 10,000 individuals. From northeastern Africa, they crossed into the Arabian Peninsula, carrying with them the accumulated knowledge of countless earlier generations, along with a genetic legacy that would eventually spread across much of the world. Research combining genetics with archaeology points most strongly toward a southern coastal route. Rather than moving deep into unfamiliar interiors, these communities appear to have followed productive shorelines where fish, shellfish, plants, and other dependable food sources could support steady travel. Their descendants reached South Asia by roughly 65,000 years ago, continued into Southeast Asia by around 60,000 years ago, and arrived in Australia by at least 50,000 years ago. Some archaeological discoveries propose an arrival as early as 65,000 years ago, although that earlier date continues to be examined and debated among researchers. Measured against the scale of continents, this movement unfolded with striking speed. Within roughly 10,000 to 15,000 years, people had traveled from Africa to Australia, crossing landscapes that stretched across much of southern Asia. The journey required adaptation to unfamiliar coastlines, changing climates, and occasional sea crossings that demanded planning and confidence upon open water. Lower sea levels during this period exposed broader coastal plains and connected many islands, although water crossings still remain necessary before reaching the Australian continent. Even modest voyages reflected growing technical skill and careful cooperation within each community. The genetic record preserves this migration with remarkable clarity. Every modern population whose ancestry lies outside Africa descends primarily from this single founding expansion. Across thousands of generations, the descendants of that comparatively small population multiplied until their shared inheritance became distributed among billions of people. The remarkable unity of this genetic signal demonstrates that, despite the extraordinary diversity seen across humanity today, much of the world traces its roots to one successful departure from Africa. The reasons behind that migration remain uncertain, and several possibilities may have worked together instead of acting alone. Growing populations could have encouraged families to explore new territories beyond familiar ranges. Improvements in stone tools, clothing, food gathering, and watercraft may have expanded the distance people could safely travel. Lower sea levels exposed coastal corridors that simplified movement along shorelines. Equally plausible is the idea that no single moment of decision existed at all. Each generation may have settled only a little farther than the last, creating a gradual expansion that became visible only across many centuries. Evidence also reveals that this was not humanity's first attempt to leave Africa. Fossils discovered in present day Israel show that anatomically modern Homo sapiens reached the region around 180,000 years ago. Those earlier populations appear to have disappeared without leaving a lasting genetic contribution to people living today. The later migration endured where the earlier journeys did not, establishing populations that continued to expand, adapt, and eventually occupy nearly every habitable region of Earth. Their footsteps became the beginning of the shared human story that continues across the planet today. The first successful migration beyond Africa did not end upon reaching Arabia. It became the beginning of a widening human presence that unfolded across connected continents over the next 30,000 years. Families expanded into new valleys, coastlines, forests, and grasslands, each generation traveling a little farther than the last. Their movement was neither a single march nor a coordinated expedition. Countless small journeys gradually linked together, carrying modern humans into environments that no member of their species had previously called home. By about 45,000 years ago, modern humans had entered Europe. Fossils discovered within Bacho Kiro Cave in present-day Bulgaria show that anatomically modern Homo sapiens had reached the continent by approximately 45,820 years ago. Europe already belonged to another human lineage. Neanderthals had occupied those landscapes for hundreds of thousands of years, adapting to shifting climates and surviving repeated ice ages. For several thousand years, the two human groups shared parts of the same continent, sometimes occupying neighboring regions and, as genetic evidence demonstrates, occasionally sharing families through interbreeding. That long coexistence eventually came to an end. Within roughly 5,000 to 10,000 years after the arrival of modern humans, Neanderthals disappeared from the fossil record. Their disappearance probably did not result from a single cause. Competition for food and territory may have reduced their opportunities for survival. Diseases carried between previously separated populations may also have played a role, while changing climates continued to reshape the landscapes both groups depended upon. Together, these pressures formed a difficult combination whose precise balance remains one of paleoanthropology's enduring discussions. Human expansion continued across the breadth of Asia. East Asia had been reached by approximately 40,000 years ago, while groups entered Siberia around 45,000 years ago, despite its demanding conditions. These northern communities adapted to long winters, seasonal migrations of animals, and landscapes shaped by ice. Their descendants eventually stood at the edge of a continent that, during colder periods, connected to another through land instead of open sea. During the last glacial maximum, sea levels fell by about 120 meters, which is about 394 feet, exposing the broad land bridge known as Beringia between Siberia and Alaska. Across this connection, the ancestors of the first Americans gradually entered a new hemisphere. The most widely accepted archaeological evidence places these first migrations between 20,000 and 15,000 years ago, although several sites in both North America and South America continue to suggest the possibility of earlier arrivals. As glaciers retreated and new pathways opened, people spread across two continents with remarkable speed, adapting to deserts, mountains, forests, and coastlines. One region remained beyond human settlement for far longer. The islands scattered across the Pacific Ocean required deliberate ocean voyages rather than travel across connected land. Beginning around 3,500 years ago, Austronesian speaking seafarers crossed enormous stretches of water using carefully built outrigger canoes. They navigated by observing stars, waves, ocean swells, clouds, and the flight patterns of birds. Their greatest achievement came with the settlement of New Zealand around the year 1280, making it the last major habitable landmass reached by our species. Within roughly 60,000 years of leaving Africa, humanity had established homes across every habitable continent, achieving a geographic expansion unmatched by any other large mammal in Earth's history. For much of humanity's story, our species was only one branch among many. Earth was shared by several different kinds of humans, each shaped by its own history, adaptations, and landscapes. At the height of this diversity, at least 9 human lineages existed across Africa, Europe, and Asia. Modern humans lived alongside Neanderthals, Denisovans, Homo erectus, Homo floresiensis, Homo luzonensis, Homo naledi, and additional populations known almost entirely through genetic evidence. The family tree of humanity was once broad, its branches extending across continents instead of narrowing toward a single surviving line. Each species occupied a different place in the changing world. Homo erectus endured for well over 1 million years, making it one of the longest-lasting human species ever to exist. Homo floresiensis survived in isolation on the Indonesian island of Flores, where limited resources favored a body standing less than 1.1 meters, which is about 3.6 feet, in height. Homo luzonensis lived on the Philippine island of Luzon, revealing that island environments repeatedly shaped distinctive human populations. Far to the south, Homo naledi occupied parts of Africa while displaying a combination of primitive and surprisingly modern characteristics that challenged straightforward ideas about human evolution. As modern humans expanded beyond Africa, these neighboring branches gradually disappeared. The pattern appears repeatedly across the archaeological record. Europe lost its Neanderthals. Much of Asia lost the Denisovans. Homo floresiensis vanished approximately 50,000 years ago during the same broad period that modern humans spread through Southeast Asia. Timing alone cannot identify a single cause, yet the repeated overlap between expanding Homo sapiens populations and declining relatives has become one of the central questions in human evolution. Some disappearances followed a different path. Homo erectus on the island of Java seems to have vanished around 110,000 years ago, before modern humans reached that region. Climate shifts, environmental transformation, and ecological pressures therefore remain the leading explanations for its extinction. This reminder encourages caution. Each human lineage experienced its own circumstances, and no single explanation fits every loss preserved within the fossil record. Researchers continue to examine several possibilities for the remaining extinctions. Competition for hunting grounds and food may have reduced already small populations. Diseases carried between previously separated groups could have spread rapidly among communities, lacking inherited resistance. Interbreeding also changed the picture. Instead of complete replacement through conflict, some populations may have been gradually absorbed as their descendants became part of expanding modern human communities. Habitat changes added further pressure, reducing the stability of regions that had supported these groups for thousands of generations. By approximately 40,000 to 10,000 years ago, those parallel human stories had come to an end. One lineage after another disappeared until only Homo sapiens remained. Their voices are absent, yet fragments of bone, stone tools, genetic inheritance, and scattered campsites continue to record their existence. Every person alive today belongs to the final surviving branch of a once diverse human family. The world that had long supported many kinds of humans became, for the first time, a planet shared by only one, carrying within its own history faint traces of all the others that came before. Every human body carries traces of earlier worlds. Muscles, bones, nerves, and reflexes did not appear all at once. Each formed as a response to challenges faced by distant ancestors, then passed from one generation to the next across millions of years. Evolution rarely begins again from an empty page. It reshapes what already exists, leaving behind structures that continue to tell stories long after their original purpose has faded. Our anatomy has become a living archive, preserving solutions to problems that vanished ages before recorded history. One of the clearest examples lies within the lower leg. A slender structure known as the plantaris muscle appears in only about 9% of modern people. For our tree-dwelling ancestors, this muscle helped flex the toes while gripping branches during climbing. Human feet gradually changed as upright walking became the dominant form of movement and the muscle lost its original role. Today, it contributes almost nothing to normal motion. Surgeons frequently remove it for tendon grafts because the body functions normally without it, preserving a small reminder of a life once spent among branches. Another inherited feature appears whenever cold air brushes the skin or strong emotion passes through the mind. Tiny muscles attached to each hair contract, producing goosebumps by lifting the hairs upright. Among mammals covered with thick fur, this reaction trapped a layer of insulating air close to the body and could also make an animal appear larger during moments of confrontation. Humans retained the same reflex even after most body hair disappeared. The response still occurs faithfully, although its original advantages have largely disappeared with the fur that once made it effective. The tailbone offers another chapter written into the skeleton. Known as the coccyx, it consists of 3 to 5 fused vertebrae that remain connected to important muscles supporting the pelvis. Even with these useful attachments, its form preserves the unmistakable signature of a tail carried by distant primate ancestors. That external appendage gradually vanished from our lineage around 25 million years ago, while the shortened foundation remained as part of the evolving skeleton. Each seated posture rests upon evidence of a feature that no longer extends beyond the body. Evolutionary history also explains one of the most remarkable detours inside the human body. The recurrent laryngeal nerve carries signals between the brain and the voice box, yet it does not travel along the shortest route. Instead, it descends into the chest, loops around the aorta, then climbs back toward the throat. In giraffes, this winding course reaches nearly 5 meters, which is about 16 feet, because the same inherited pathway stretched as the neck lengthened across countless generations. The arrangement began in fish ancestors, where the nerve followed a direct path around structures that later evolved into parts of the neck and chest. Evolution modified the body around that pathway instead of redesigning it from the beginning. The eyes preserve one final inheritance, unlike those of any other great ape. Humans display broad white sclera surrounding the colored iris, making another person's gaze remarkably easy to follow. A brief glance can reveal attention, intention, or shared focus without a single spoken word. This feature likely strengthened cooperation by allowing groups to coordinate through common visual attention. Even in the smallest movements of our eyes, the body still carries the imprint of an evolutionary journey measured not in generations alone, but across millions of years. No artifact reveals the first spoken sentence. Stone survives, bones endure, and traces of fire remain long after their flames fade, yet language leaves almost nothing behind for archaeology to recover. Its earliest history must instead be assembled from the shape of ancient skulls, the pathways of nerves, inherited genes, and comparisons with the living relatives that share our evolutionary roots. The most influential invention our species ever possessed arrived almost without a physical signature, even though its consequences eventually reshaped every corner of human existence. Among the clues preserved within our cells is a gene known as forkhead box protein, P2, often described as the language gene because of its role in the fine control of movements required for speech. Humans carry a version that differs from chimpanzees at two specific positions, changes believed to have become established throughout the human lineage around 200,000 years ago. Even more revealing, Neanderthals carried the same human form of this gene. That shared inheritance suggests the biological foundations of spoken communication emerged before our own species stood alone upon the landscape. Genes alone could never produce speech without a body capable of shaping sound. The human voice depends upon several anatomical features working together with remarkable precision. A lowered voice box creates the longer vocal tract needed for forming a wide range of vowel sounds. Delicate control of breathing regulates rhythm and emphasis, while intricate muscles of the tongue shift constantly to produce distinct consonants and vowels. The canal, carrying the nerve that directs tongue movement, also displays modern characteristics in Homo heidelbergensis and Neanderthals. These combined features indicate that the physical ability for complex speech appeared well before anatomically modern humans spread across the world. What transformed language into something entirely different from every other communication system was not merely sound, but the ideas carried within it. Humans could describe places beyond the horizon and events remembered from distant seasons. They could imagine futures that had not yet unfolded and discuss people who were absent or long deceased. One thought could rest inside another, allowing stories, plans, beliefs, and explanations to grow layer upon layer without losing coherence. Knowledge no longer depended entirely upon direct experience. Discoveries made by one generation could pass intact to the next, expanding steadily instead of beginning anew with every birth. This accumulation produced an extraordinary treasury within every human mind. An educated adult commonly understands between 40,000 and 60,000 words. Each carries more than a simple definition. Words connect ideas, distinguish subtle differences, preserve exceptions, express relationships, and gather meanings refined through countless conversations across many generations. A child entering the world inherits this immense collection without carving it from nature alone. Every spoken lesson adds another thread to a fabric woven across thousands of years of shared experience. Language also altered humanity's relationship with mortality. Before stories could travel beyond a lifetime, memory faded with those who carried it. Spoken names allowed absent people to remain present within the minds of others. Children came to know grandparents they had never seen through voices that preserved their deeds, choices, and character. In this way, each generation extended the lives of those before it through remembrance. History began not with ink or carved stone, but with words carried from one person to another, keeping both knowledge and lives alive beyond the limits of a single human lifetime. A carved figure can hold far more than the shape cut into its surface. At some point during humanity's long story, the mind acquired the ability to let one object stand for another, allowing stone, ivory, pigment, and sound to carry meanings that existed beyond their physical form. This capacity marked a profound transformation. An animal painted upon a cave wall was no longer only an animal. It could become a memory, a hope, a lesson, or part of a story shared among people who understood the same symbols. From that point onward, imagination could leave durable traces upon the world. This symbolic ability appeared across remarkable distances. Among its best known expressions are the Venus figurines, small carved representations of women discovered from Western Europe to the plains of what is now Russia. Created between roughly 35,000 and 11,000 years ago, these figures display striking similarities despite being separated by thousands of kilometers, which is about 1,864 miles. Their repeated forms suggest that different communities shared related symbolic traditions or ritual ideas, even without sustained direct contact. The carvings were never exact portraits. Instead, they emphasized particular features with deliberate consistency, hinting that their importance rested within meaning rather than appearance alone. Another creation carried imagination even further. Around 40,000 years ago, artisans in what is now southern Germany shaped a mammoth ivory tusk into a figure known today as the Lion Man of Hohenstein-Stadel. It combined the body of a human with the head of a lion, depicting a being that had never walked across the earth. Such an image required a mind capable of blending separate realities into something entirely new. It stands as the oldest known representation of a creature born from imagination alone, offering one of the earliest surviving glimpses of mythology and the ability to think beyond direct observation. The same symbolic capacity also appeared in the treatment of the dead. Both Neanderthals and Homo sapiens placed bodies into prepared graves under certain circumstances, indicating that death had acquired significance extending beyond physical loss. Whether these burials reflected remembrance, spiritual belief, or social tradition remains uncertain. Their existence nevertheless reveals minds capable of contemplating possibilities that could neither be touched nor confirmed through ordinary experience. The visible world had become connected to ideas that existed only within thought. Music belongs within this expanding landscape of symbolism. Flutes carved from bird bones and mammoth ivory, discovered in Germany and dating to around 40,000 years ago, are the oldest confirmed musical instruments yet found. Their craftsmanship suggests that musical expression was already well established. Long before carved instruments appeared, the human voice, rhythmic movement, clapping hands, and simple percussion likely filled gatherings with patterns of sound that strengthened memory and cooperation. Rhythm required no permanent object, only minds capable of sharing time together. Every inhabited continent eventually produced art, music, ritual, and symbolic traditions, even where communities remained separated for thousands of years. Such consistency suggests these expressions did not arise as isolated cultural inventions. They emerged from a biological capacity carried within Homo sapiens wherever people settled. Different landscapes inspired different creations, yet the impulse remained recognizably the same. The symbolic mind became another inheritance of our species, allowing ideas to travel beyond individual lives and giving imagination a lasting place beside survival itself. For most of the existence of anatomically modern humans, life unfolded through movement. Families followed the changing seasons, returning to familiar valleys, rivers, and grasslands as plants ripened and animal herds shifted across the landscape. Food came from many different sources, including fruits, roots, nuts, fish, shellfish, birds, and game. Communities remained relatively small, often numbering only a few dozen people whose knowledge of the land allowed them to thrive without permanent settlements. This pattern endured for well over 200,000 years before another way of living gradually appeared. Agriculture did not begin in one place or through one remarkable discovery. Across different continents, separate communities slowly learned that certain plants could be encouraged to grow near their homes. In the region known as the Fertile Crescent, people cultivated the ancestors of wheat, barley, and lentils. Elsewhere, rice and millet became important crops in Eastern Asia, while maize and squash emerged in Mesoamerica. Potatoes and quinoa were domesticated in the Andes, and sorghum, together with pearl millet, became valuable across parts of sub-Saharan Africa. Each region followed its own path, shaped by local climates, landscapes, and wild species. The Fertile Crescent possessed an unusual combination of advantages. Wild grasses with large, nutritious seeds grew in abundance, while sheep, goats, pigs, and cattle lived nearby and could eventually be domesticated. Seasonal rainfall encouraged predictable cycles of growth, allowing repeated harvests from the same landscapes. Generation after generation, people gathered the plants that were easiest to collect. Without intending to reshape evolution, they favored seeds that remained attached to their stalks, ripened together, and gradually became larger. Those traits spread through cultivated fields until many crops depended almost entirely upon human care for their survival. The harvests became increasingly dependable, yet this transformation carried significant biological costs. Studies of ancient skeletons reveal that many early farming communities were shorter than the hunter-gatherers who lived before them. Narrower diets often reduced nutritional diversity, contributing to iron deficiency, anemia, and other health problems. Teeth also preserved evidence of change. Greater reliance on carbohydrate-rich foods increased tooth decay and dental disease. Permanent villages brought people livestock, and stored food into close contact, creating favorable conditions for infectious illnesses that spread more easily than they had among mobile groups. Despite these burdens, farming reshaped the future because it produced far more food from the same area of land. A single hectare of cultivated ground, which is about 2.5 acres, could support many more people than an equivalent area left in its natural state. Larger harvests allowed populations to expand, villages to grow into towns, and generations to remain in one place long enough to build lasting traditions. Skills became increasingly specialized as some individuals devoted themselves to pottery, weaving, construction, trade, or leadership, while others continued producing food. The agricultural revolution, therefore, represented both gain and sacrifice. Human societies accepted poorer health in many respects while receiving greater numbers, permanent settlements, and an expanding capacity to store knowledge across generations. Fields gradually replaced many wild landscapes, and the rhythm of daily life became tied to planting and harvest. From that enduring exchange emerged the foundations of cities, kingdoms, written history, and the interconnected world that would follow. Long before fields became permanent features of the landscape, another transformation had already begun beside human campfires. It unfolded through countless ordinary encounters between people and wild creatures, each generation altering the next by the smallest of margins. Among those animals, one would become an enduring companion. Genetic evidence indicates that the partnership between humans and dogs began at least 15,000 years ago and may extend as far back as 40,000 years, making it older than agriculture itself, and one of the earliest relationships between our species and another large mammal. The beginning of that partnership was likely shaped less by deliberate planning than by opportunity. Some gray wolves proved more tolerant of human presence than others. These individuals approached camps where discarded bones and scraps offered reliable meals. Those with calmer temperaments survived more successfully around people and passed those traits to their offspring. Across many generations, natural selection favored wolves that could coexist with humans. Only later did people begin choosing which animals should breed, gradually strengthening characteristics such as cooperation, attentiveness, and reduced aggression. The result was not merely a tamed wolf, but an entirely new animal whose future became closely tied to our own. As villages expanded, attention turned toward larger creatures that could provide dependable sources of food and labor. Among the most important was the wild aurochs, an immense ancestor of modern cattle that stood nearly 2 meters at the shoulder, which is about 6 feet 7 inches. Powerful, fast, and capable of defending itself against formidable predators, the aurochs represented a dangerous challenge. Around 10,500 years ago, communities in the Fertile Crescent began breeding selected individuals, gradually transforming a fierce wild animal into herds suited for life alongside people. The original aurochs eventually vanished, with the final known individual dying in Poland during the 17th century within a protected royal hunting preserve, leaving only its domesticated descendants. Living beside cattle introduced a new source of nourishment, yet it also reshaped human biology. Across nearly all mammals, the enzyme called lactase declines after infancy, making the sugar found in milk difficult to digest during adulthood. Most people around the world still follow that ancestral pattern. In several populations with long traditions of cattle herding, however, genetic mutations allowed lactase production to continue throughout life. These changes appeared within roughly 7,500 years, representing one of the clearest and fastest examples of natural selection documented in modern humans. Culture altered the environment, and the altered environment favored new biological traits, creating an ongoing conversation between inheritance and daily life. Another partnership extended that conversation across entire continents. Horses were domesticated on the Eurasian steppe around 5,500 years ago, providing speed unlike anything previously available. Journeys that once required many days became far shorter. Trade routes expanded, ideas traveled farther, and communication connected distant communities with increasing frequency. Mounted travel also transformed warfare, allowing armies to move across remarkable distances with unprecedented mobility. Many researchers believe these developments contributed to the remarkable spread of the Indo European language family throughout Europe and much of Asia, carried alongside generations of riders whose lives became inseparable from the animals that bore them across open grasslands. Domestication reshaped more than individual species. It redirected evolution itself, binding the destinies of humans and countless animals into a shared history that continues to unfold with every generation. Before words could be preserved on stone or clay, every memory depended upon a living voice. Knowledge traveled from one generation to the next through conversation, song, ritual, and careful repetition. Elders carried the experience of many decades, and every passing season entrusted them with another layer of understanding. Their memories guided planting, navigation, craftsmanship, and tradition. When one life came to its end, countless details of the world disappeared with it, leaving those who remained to rebuild what could be remembered. Across different civilizations, people gradually discovered another way to preserve thought. Writing emerged independently in several regions, including Mesopotamia, Egypt, China, and Mesoamerica. Each tradition developed its own symbols, materials, and methods without borrowing from the others. Although these systems looked remarkably different, they answered the same practical challenge. Growing societies required information that could survive beyond conversation alone. Permanent settlements produced harvests, trade, taxation, and administration on a scale that memory could no longer manage with complete reliability. The earliest surviving written records reveal a surprisingly practical beginning. Rather than preserving legends or poetry, many of the oldest clay tablets from Mesopotamia listed quantities of grain, counted livestock, and recorded commercial exchanges. Agricultural abundance created responsibilities that demanded careful bookkeeping. Fields yielded more food than immediate families could consume. Storehouses collected supplies, and communities needed dependable records of ownership and distribution. The pressure to organize these growing resources encouraged the invention of writing long before it became a tool for philosophy or literature. Once ideas could be preserved outside the human mind, knowledge entered an entirely different relationship with time. A written record remained unchanged whether its creator lived another year or another century. Instructions, observations, and agreements could travel across remarkable distances without relying upon imperfect recollection. Information no longer depended entirely upon memory, allowing discoveries to accumulate instead of beginning again whenever experienced individuals passed away. Each generation inherited not only stories, but carefully preserved observations from people they would never meet. This transformation reshaped civilization as profoundly as agriculture itself. Mathematics, astronomy, medicine, engineering, and government all benefited from records that could be consulted repeatedly without alteration. Scholars compared observations separated by many generations, identifying patterns too gradual for any single lifetime to witness. Written archives also encouraged accountability, preserving laws, treaties, and contracts in forms that communities could examine long after they were first created. Memory expanded beyond biology into libraries, temples, workshops, and schools where accumulated knowledge continued growing through successive generations. Another remarkable development followed with the invention of the alphabet in the ancient Levant, roughly 3,800 years ago. Earlier writing systems often required hundreds of symbols representing entire words or syllables. Alphabetic writing reduced this complexity by assigning a small collection of symbols to individual speech sounds. Learning became far more accessible, and literacy gradually spread beyond specialized scribes. From that original innovation descended the alphabetic systems used across much of the world today, including Latin, Greek, Arabic, Hebrew, and Cyrillic. Writing achieved something no earlier invention had fully accomplished. It separated knowledge from the fragile limits of individual memory, allowing human experience to endure across centuries. A thought formed within one mind could outlive its creator, crossing continents and generations until it reached readers living in worlds the original writer could never have imagined. Evolution is often imagined as a story that ended once people built cities, cultivated fields, and surrounded themselves with the inventions of civilization. The evidence preserved within the human genome tells a different story. Natural selection did not disappear as history unfolded. It continued to shape populations whenever new environments, diets, diseases, or ways of living altered the conditions of survival. The last 10,000 years contain some of the clearest examples of rapid human evolution ever identified, revealing that our species remains part of the same biological process that guided every chapter before it. One familiar example has already appeared in the story of domesticated animals. Most young mammals produce the enzyme lactase only during infancy, allowing them to digest the sugar found in milk. Production normally declines after weaning. In several human populations with long traditions of cattle herding, however, genetic changes allowed lactase production to continue throughout adulthood. This adaptation spread through parts of Europe, Eastern Africa, and the Middle East within roughly 7,500 years, an exceptionally brief span in evolutionary history, demonstrating how powerful natural selection can become when a new food source provides a consistent advantage. Agriculture also reshaped another force of evolution through an unexpected path. Permanent settlements and irrigation created pools of standing water where mosquitoes flourished. As malaria spread, individuals carrying a single copy of the sickle cell genetic variant gained substantial protection against the disease. Those inheriting two copies developed sickle cell anemia, a severe inherited disorder, while those with one copy often survived malaria more successfully than their neighbors. Across parts of Western Africa, the Mediterranean region, and South Asia, this balance between benefit and cost increased the frequency of the variant within roughly 5,000 years, leaving a lasting signature of selection driven by changing landscapes. High mountain plateaus presented a different challenge. The air above 4,000 meters, which is about 13,123 feet, contains much less oxygen than at sea level. Populations living for thousands of years on the Tibetan Plateau acquired genetic variants that allow their bodies to use oxygen efficiently without producing unusually thick blood. Among these adaptations is a version of a gene inherited from the Denisovans, showing that encounters between different human groups contributed useful biological solutions. These variants became common among Tibetans, while remaining rare among the closely related Han Chinese population, illustrating how evolution can proceed rapidly when environments impose persistent demands. Skin pigmentation continued to respond to geography after modern humans dispersed across the world. Populations living beneath intense equatorial sunlight generally retained or evolved darker skin, helping protect folate and reducing damage from ultraviolet radiation. Groups settling in regions with weaker sunlight gradually evolved lighter skin, improving the production of vitamin D. These changes unfolded repeatedly in different populations during the past 50,000 years and remain part of an ongoing process rather than a completed transformation. Even recorded history carries evidence of natural selection. Repeated outbreaks of bubonic plague altered the genetic landscape of Europe by increasing the frequency of certain immune system variants among survivors. Similar processes continue wherever diseases influence survival and reproduction. The human story therefore remains unfinished, with every generation carrying both the inheritance of countless ancestors and the possibility of future change written into the living fabric of life itself. Every cell within the human body carries an archive so compact that it can rest inside a microscopic nucleus, yet detailed enough to preserve the story of an entire species. That archive is deoxyribonucleic acid. It is not a written history in the ordinary sense, yet every generation leaves faint traces within it, allowing modern science to reconstruct journeys that vanished from memory thousands of years before the first written records appeared. The first complete reading of the human genome, completed through the Human Genome Project in 2003, after years of international collaboration and a cost of roughly $2.7 billion, transformed the study of human origins. Researchers discovered that humans possess only about 20,000 to 25,000 protein coding genes. That total came as a surprise. A tiny water flea contains even more protein coding genes, while a small nematode worm carries a similar number. The richness of the human mind, body, and society, therefore, does not arise from having an unusually large collection of genes. Instead, much of human complexity emerges from the intricate system that determines when particular genes become active, where they operate within the body, and how strongly they are expressed. The genome behaves less like a rigid architectural drawing and more like a responsive instruction library, adjusting its activity according to developmental stages, surrounding tissues, and environmental conditions. The same collection of genes can therefore contribute to remarkably different outcomes depending upon how those instructions are regulated throughout life. Another revolution arrived when researchers learned to recover deoxyribonucleic acid from ancient bones and teeth. During roughly the past 15 years, advances in sequencing technology have made it possible to examine the genomes of people who lived tens of thousands of years ago. These genetic records have revealed migrations, encounters, and population changes that left almost no visible trace in artifacts or fossils alone. Skeletons once known only through their shape can now speak through their inherited code, offering direct evidence of relationships across continents and across immense stretches of time. Among the most remarkable discoveries concerns Europe during the Bronze Age, about 5,000 years ago. Genetic evidence shows that the people living across much of Europe before this period differed substantially from later populations. A large migration arrived from the Pontic-Caspian steppe, carrying ancestry that today remains widespread across Eastern Europe and Central Asia. Within only a few centuries, these pastoral communities contributed much of the genetic foundation of later European populations. They also appear to have spread the ancestral form of many languages that would eventually diversify across much of Europe and large regions of Asia. Perhaps the most striking lesson of all comes from comparing living people with our closest relatives. A single community of chimpanzees living within one forest in Western Africa contains more genetic variation than the entire human population spread across Earth. This remarkable similarity among humans reflects our relatively recent origin from a modest founding population in Africa, followed by repeated population bottlenecks as groups expanded into new lands. Even the two most distantly related people alive today remain connected by only about 3,500 generations, or roughly 70,000 years, making every person on Earth a close relative within the larger history of life. Nothing in the human story can be traced to a single miraculous step. No bone, organ, or isolated behavior transformed one primate into a species capable of reshaping an entire planet. The difference emerged through a sequence of changes that reinforced one another across millions of years. Each adaptation created opportunities that had never existed before, allowing another adaptation to follow. Taken alone, each step appears modest. Joined together, they formed a chain of consequences unlike anything else in the history of life. Walking upright released the hands from the constant demands of movement. Those free hands could carry food, shape stone, gather useful materials, and eventually fashion tools with increasing precision. Better tools improved access to meat, marrow, and other nutrient-rich foods. Cooking unlocked still more energy by making many foods easier to digest. That richer diet helped support the growing metabolic demands of an expanding brain. As brains became larger and more capable, communication grew increasingly sophisticated until language emerged as a flexible system for sharing knowledge across individuals and generations. Each innovation strengthened the next, producing a cascade in which every gain multiplied the value of those that had come before. This process reached a turning point with cumulative culture, sometimes described as the ratchet effect. Once a useful discovery entered the shared knowledge of a community, it no longer needed to be reinvented by every new generation. Children inherited solutions created by parents, grandparents, and distant ancestors, then refined those solutions before passing them onward. Progress no longer depended entirely upon biological evolution. Cultural knowledge accumulated while remaining available to those who followed, allowing improvements to build steadily over time instead of repeatedly returning to the beginning. The inheritance received by a child today reflects this remarkable accumulation. Every newborn arrives carrying the biological legacy of roughly 300,000 years of modern human evolution, while also entering a world shaped by countless generations of invention. Spoken language, mathematics, agriculture, medicine, engineering, and scientific understanding all exist before that child speaks a first word. None of this knowledge is encoded directly within the genome. It survives because communities preserve it, teach it, and expand it, allowing each generation to begin far beyond the starting point of the previous one. Another essential ingredient lies within the remarkable human ability to imagine the thoughts of another mind. This capacity, known as theory of mind, allows people to anticipate intentions, recognize beliefs, interpret emotions, and predict behavior with extraordinary subtlety. It supports teaching, cooperation, empathy, negotiation, persuasion, and even deception. Other animals display simpler forms of social awareness, yet the human version reaches a depth that supports relationships among thousands, even millions, of individuals who may never meet. When theory of mind joined with language, cooperation expanded beyond families and familiar companions. People became able to organize around ideas that existed only because many individuals accepted them together. Money carries value through shared agreement. Laws exist because communities recognize their authority. Nations, religions, institutions, and countless social systems depend upon collective belief maintained through communication. These invisible frameworks allow strangers to trust one another, exchange resources, and pursue common goals across continents. From countless small evolutionary changes emerged a species whose greatest strength was never a single adaptation, but the multiplying power created when each advantage became the foundation for the next. Success can be measured in many ways, yet evolution recognizes only one enduring result: the ability of a lineage to persist, spread, and leave descendants. By that measure, Homo sapiens has become one of the most successful large mammals ever to walk the earth. From a founding population that may have numbered only a few thousand individuals around 70,000 years ago, communities gradually expanded across every continent except Antarctica. Forests, deserts, mountain ranges, islands, and frozen coastlines all became places where human life could take root. No earlier member of our family achieved such reach, and few species of any kind have reshaped their surroundings so completely. The path toward that success carried consequences that no earlier stage of the journey could have anticipated. The abilities that once helped small bands survive changing climates eventually transformed entire landscapes. Forests gave way to fields, rivers were redirected, and countless species found themselves sharing a planet with an organism capable of altering environments at remarkable speed. Many researchers now recognize the present decline in biodiversity as the sixth great mass extinction in Earth's history, driven primarily by human land use, hunting, and climate change. The same intelligence that expanded opportunity also amplified influence beyond anything previously seen among mammals. Long before cities rose or written records preserved memory, traces of this influence had already entered the fossil record. As humans reached new continents, many large animals vanished within spans that were brief in geological time. Mammoths, mastodons, woolly rhinoceroses, giant ground sloths, giant kangaroos, and numerous other giants disappeared after the arrival of skilled human hunters. Africa remained the major exception. There, large animals had shared their homeland with evolving human ancestors for immense stretches of time, allowing caution and defensive behavior to develop alongside increasingly capable predators. Elsewhere, unfamiliar encounters unfolded with far less opportunity for adaptation. Viewed across deep time, the contrast carries an unusual irony. The capacities that allowed cooperation among unrelated people, the sharing of knowledge through language, and the steady accumulation of culture ultimately produced a force capable of transforming the biosphere itself. The present rate of species loss exceeds what would normally be expected across comparable intervals of natural history, unfolding within centuries, instead of the many thousands of years associated with earlier global biological crises. A mind shaped to improve survival gradually became powerful enough to influence the evolutionary future of countless other forms of life. Another contrast emerges within the human mind itself. The brain that proved so effective during the Pleistocene evolved to manage immediate dangers, personal relationships, and decisions whose consequences unfolded across days or seasons. Modern civilization now asks that same brain to understand changes developing over decades and centuries, to weigh the needs of billions of strangers, and to coordinate action across continents. Evolution produced remarkable flexibility, yet it could not anticipate every challenge created by its own success. None of this stands as praise or condemnation. It is an observation drawn from the long arc of evolution itself. The qualities that carried an upright ape from scattered African landscapes to global civilization remain the same qualities shaping the world today. Within that continuing story rests one of nature's most profound paradoxes, a species transformed by evolution that now possesses the power to transform evolution in return. 6 million years ago, a small population of African apes followed a path that no living creature could have imagined. Across countless generations, each small change rested upon those that came before, until one branch of that ancient family learned to shape stone, master fire, speak through language, preserve memory in writing, and finally look back across deep time to understand its own beginnings. The same lineage has sent spacecraft beyond the solar system, read the genomes of long vanished relatives, covered cave walls on 4 continents with enduring images, and created mathematics, philosophy, and science to explore the universe as well as itself. Every person alive today carries that immense history within a single body. The spine bears the mark of ancestors who stood upright. The pelvis reflects the long commitment to walking on 2 legs. Hands once devoted to climbing became instruments of remarkable precision. Above them rests a skull reshaped to contain a brain that expanded dramatically across roughly 2 million years, supporting imagination, memory, planning, and the ability to share ideas across generations. None of these features appeared all at once. Each emerged through innumerable lives, each contributing a small chapter to a story far older than any civilization. The search for human origins reaches beyond curiosity alone. It reveals a species whose survival depended again and again upon learning from experience, adapting to unfamiliar landscapes, cooperating with others, and preserving knowledge. Along that journey came moments when human numbers fell dangerously low, yet each recovery carried forward the accumulated inheritance of those who endured. Long before written history, people honored their dead, covered stone walls with images of living creatures, crafted music, and spoke words whose echoes disappeared into the air, while their meaning endured through memory and tradition. Among the millions of species that have lived upon Earth across 4 billion years of evolving life, only one has uncovered its own ancestry through fossils, genetics, archaeology, and careful observation. Rocks became archives, bones became witnesses. The genetic library contained within every living cell revealed relationships hidden for countless generations. Piece by piece, humanity assembled a narrative extending across millions of years, connecting living people with ancestors whose names will never be known, but whose choices remain visible in every step taken today. The forest dwelling apes living 6 million years ago possessed no glimpse of what their descendants would accomplish. The Australopithecines crossing fresh volcanic ash left footprints without knowing they would be discovered millions of years later by minds sharing the same upright stride. The small groups who survived periods of extreme hardship could not foresee descendants numbering in the billions, living across every continent, studying stars whose light began its journey before humanity itself existed. The next chapter remains unwritten because it belongs to those who are living it now. The fossil record ends where the present begins. Even so, the long journey from forest ape to global civilization offers one enduring observation. Again and again, survival favored curiosity, cooperation, resilience, and the ability to learn from the past. Those qualities carried humanity across changing climates, unfamiliar seas, and countless generations. They remain part of the same story today, a story still unfolding beneath the same sky that watched its first uncertain steps.